Hello and welcome to Calculus 1. This is Lesson 1, Intro to Limits. Before we write a single integral or a single derivative, we have to start with the one idea that underpins everything else. It's an idea that might seem a little strange at first, a little philosophical, but it is the engine of all of calculus. That idea is the limit. So, what is a limit? Let me start with a paradox. Imagine you shoot an arrow at a target. To get to that target, the arrow must first travel half the distance. Then from there, it must travel half of the remaining distance. And from there, half of that new remaining distance, and so on, forever and ever. If you keep dividing the remaining distance in half, it seems like the arrow can never actually reach its destination. This is a classic puzzle called Zeno's paradox. And while it feels like a brain teaser, it touches on a fundamental problem in math. How do we deal with the concept of getting infinitely close to something? That is what a limit is for. A limit isn't about being at a destination, it's about the journey approaching that destination. Let's start with an easy case. Consider the function f of x equals x plus 2, a simple, straight line. What if I ask, what is the limit of f of x as x approaches 3? This is just asking, as our x value gets closer and closer to 3, what y value does the function get closer and closer to? Well, we can just plug it in. F of 3 equals 3 plus 2, which equals 5. The graph is a continuous line with no tricks or holes. As x gets closer to 3, the y value gets closer to 5, so the limit is 5. This is called finding a limit by direct substitution, and it works for a lot of well-behaved functions like simple polynomials. But the real power of limits shines when direct substitution doesn't work. Let's look at a trickier function. F of x equals x squared minus 4 divided by x minus 2. What is our forbidden spot here? Look at the denominator. If we try to plug in x equals 2, we get 2 minus 2, which equals 0. But we can't divide by 0 in math. The function is undefined at x equals 2 is what that means. But we can find the limit as x approaches 2. We can ask, where is the function headed towards? Let's sneak up on x equals 2 from both sides. So we're going to plug in numbers that are very close to 2. So f of 1.9 will leave you with 3.9. F of 1.99 leaves you with 3.99. Now let's look at the function from the right. F of 2.1 equals 4.1. F of 2.01 equals 4.01. So from the right side, we can conclude that we are also heading toward the y value of 4. The graph of this function looks just like the line y equals x plus 2, but with a tiny hole at the coordinates 2, 4. A limit does not care about that hole. It only cares about the path leading towards it. Since the path from both sides leads to the same destination, the limit is 4. This idea of checking from the left and the right is so important that it has its own name, one-sided limits. The limit as x approaches 2 from the left is written as lim as x approaches 2 with a negative sign above the 2 of f of x equals 4. The limit as x approaches 2 from the right is written as lim as x approaches 2 with a plus sign to the right of the 2 of f of x equals 4. This leads us to the single most important rule for the existence of a limit. A limit exists if and only if the left-hand limit equals the right-hand limit. Since our left-hand limit, 4, equals our right-hand limit, 4, the overall limit exists and is 4. So that leaves us with the question, when do limits not exist? So if the left and right sides have to match, what happens when they don't? Then the limit does not exist, or DNE. This happens in 3 common ways. A jump, which is considered a piecewise function where f of x equals -1 for x is less than 0 and f of x equals 1 for x is greater than or equal to 0. That means that the left-hand limit at x equals 0 is -1, the right-hand limit at x equals 0 is +1, and since -1 does not equal +1, The overall limit does not exist. Unbounded behavior. What about the function f of x equals 1 divided by x squared as x approaches 0? From both the left and the right, the function's value shoots up towards positive infinity. Because the function doesn't approach a specific finite number, the limit does not exist. Infinite oscillation. Look at f of x. It equals sine over 1 of x. As x approaches 0, the function oscillates wildly between -1 and 1, faster and faster. It never settles on a single value, so the limit does not exist. So what if I'm given a graph of a limit and am expected to read it? Being able to look at a graph and instantly see the limit is a crucial skill in calculus. Let's break down this graph of f of x. The easy point at x equals -4. The graph is a solid continuous line at x equals -4. There are no holes or jumps or anything. The point is at -4, 2. The limit is simply the function's value. Case number 2, the open hole at x equals -1. There's a clear hole in the graph here. The function's value, f of -1, is undefined because of that hole, but the limit only cares about the path. From the left, the path heads towards a y value of 3. From the right, the path also heads towards a y value of 3. Since the paths match, the limit does exist. Case number 3, the plugged hole. These are the trickiest cases, so you have to be careful. For this graph, we have a hole at 3, 1 and a solid dot at 3, 4. The function's value is where the solid dot is, so f of 3 equals 4. The limit is about the path, not the dot. The dot is a distraction. From the left, the path heads towards the hole at a y value of 1. From the right, the path also heads towards the hole at a y value of 1. Therefore, the limit is 1. This shows the critical difference. The value of the function and the limit at a point can be different. Let's recap the big ideas. It's about the journey, not the destinations. Limits are about the y value you approach, not necessarily the y value that exists at a point. The two sides must agree. For a limit to exist, then the left-hand limit must equal the right-hand limit. 3 ways to fail. A limit does not exist if there is a jump, unbounded behavior, or wild oscillation. In the next lessons, we'll learn algebraic tricks to solve limits without needing a graph or a calculator. If this video has helped you, please like and subscribe. Thanks for watching.